Dynamic programming. We begin our study of algorithmic techniques with greedy algorithms, which in some sense form the most natural approach to algorithm design. Faced with a new computational problem, we've seen that it's not hard to propose multiple possible greedy algorithms. The challenge is then to determine whether any of these algorithms provides a correct solution to the problem in all cases. The problems we saw in Chapter 4 were all unified by the fact that, in the end, there really was a greedy algorithm that worked. Unfortunately, this is far from being true in general. For most of the problems that one encounters, the real difficulty is not in determining which of several greedy strategies is the right one, but in the fact that there is no natural greedy algorithm that works. For such problems, it is important to have other approaches at hand. Divide and conquer can sometimes serve as an alternative approach, but the versions of divide and conquer that we saw in the previous chapter are often not strong enough to reduce exponential brute force search down to polynomial time. Rather, as we noted in chapter 5, the applications there tended to reduce a running time that was unnecessarily large, but already polynomial, down to a faster running time. We now turn to a more powerful and subtle design technique, dynamic programming. It will be easier to say exactly what characterizes dynamic programming after we've seen it in action, but the basic idea is drawn from the intuition behind divide and conquer and is essentially the opposite of the greedy strategy. One implicitly explores the space of all possible solutions by carefully decomposing things into a series of subproblems and then building up correct solutions to larger and larger subproblems. In a way, we can thus view dynamic programming as operating dangerously close to the edge of brute force search. Although it's systematically working through the exponentially large set of possible solutions to the problem, it does this without ever examining them all explicitly. It is because of this careful balancing act that dynamic programming can be a tricky technique to get used to. It typically takes a reasonable amount of practice before one is fully comfortable with it. With this in mind, we now turn to a first example of dynamic programming, the weighted interval scheduling problem that we defined back in section 1.2. We are going to develop a dynamic programming algorithm for this problem in two stages. First, as a recursive procedure that closely resembles brute force and then by reinterpreting this procedure as an iterative algorithm that works by building up solutions to larger and larger subproblems. Weighted interval scheduling a recursive procedure. We have seen that a particular greedy algorithm produces an optimal solution to the interval scheduling problem, where the goal is to accept as large a set of non-overlapping intervals as possible. The weighted interval scheduling problem is a strictly more general version in which each interval has a certain value or weight and we want to accept a set of a maximum value. Designing a recursive algorithm. Since the original interval scheduling problem is simply the special case in which all values are equal to 1, we know already that most greedy algorithms will not solve this problem optimally. But even the algorithm that worked before, repeatedly choosing the interval that ends earliest, is no longer optimal in the more general setting, as the simple example in figure 6.1 shows. Indeed, no natural greedy algorithm is known for this problem, which is what motivates us switch to dynamic programming. As discussed above, we will begin our introduction to dynamic programming with a recursive type of algorithm for this problem, and then in the next section, we'll move to a more iterative method that is closer to the style we use in the rest of this chapter. We use the notation from our discussion of interval scheduling in section 1.2, we have n requests labeled 1 to 3 until n, with each request I specifying a start time Si and a finish time Fi. Each interval I now also has a value or weight Vi. Two intervals are compatible if they do not overlap. The goal of our current problem is to select a subset S, which is a subset equals to the set from 1 to 3 until n of mutually compatible intervals, so as to maximize the sum of the values of the selected intervals, that is, the summations of Vi summing for all I in such a subset S. Let's suppose that the requests are sorted in order of non-decreasing finish time. That is, F1 is less than or equals to F2, which is less than or equals to F3, and so on, which is less than or equals to Fn. We will say a request I comes before a request J if I is less than J. This will be the natural left to right order in which we'll consider intervals. So help in talking about this order, we define a P of J for an interval J to be the largest index I, which is less than J, such that intervals I and J are disjoint. In other words, I is the leftmost interval that ends before J begins. We define P of J equals to 0 if no request I less than J is disjoint from J. An example of the definition of P of J is shown in figure 6.2. Now, given an instance of the weighted interval scheduling problem, let's consider an optimal solution O, ignoring for now that we have no idea what it is. Here is something completely obvious that we can say about O. Either interval n, the last one, belongs to O, or it doesn't. Suppose we explore both sides of this dichotomy a little further. If n is in O, then clearly no interval indexed strictly between P of n and n can belong to O, because by the definition of P of n, we know that intervals P of n plus 1, P of n plus 2, and so on until n minus 1 all overlap interval n. Moreover, if n is in O, then O must include an optimal solution to the problem consisting of requests, the set 1 to 3 until P of n, for if it didn't, we could replace O's choice of requests from 1 to 3 until P of n with a better one, with no danger of overlapping request n. On the other hand, if n is not in O, the optimal solution, then O is simply equal to the optimal solution to the problem consisting of requests from the set 1 to 3 until n minus 1. This is by completely analogous reasoning. We are assuming that O does not include the request n, so if it does not choose the optimal set of requests from the set 1 to 3 until n minus 1, we could replace it with a better one. All this suggests that finding the optimal solution on intervals of the set 1 to 3 until n involves looking at the optimal solutions of smaller problems of the form 1 to 3 until j. Thus, for any value of j between 1 and n, let Oj denote the optimal solution to the problem consisting of requests of the set 1 to 3 until j, and let opt of j denote the value of this solution. We define opt of 0 equals to 0 based on the convention that this is the optimum over an empty set of intervals. The optimal solution we're seeking is precisely On with a value opt of n for the optimal solution Oj on the set 1 to 3 until j. Our reasoning above, generalizing from the case in which j equals to n, says that either j is in Oj, in which case opt of j is equals to Vj plus opt of P of j, or j is not in Oj, in which case opt of j is equals to opt of j minus 1. Since these are precisely the two possible choices, that is, either j is in Oj or j is not in Oj, we can furtherly say that 6.1 opt of j is equals to the maxima chosen between Vj plus opt of P of j or OPT of j minus 1. And how do we decide whether n belongs to the optimal solution of j? This too is easy. It belongs to the optimal solution if and only if the first of the options above is at least as good as the second. In other words, 6.2, request j belongs to an optimal solution on the set 1 to 3 until j if and only if Vj plus optimal of P of j is greater than or equals to OPT of j minus 1. These are facts from the first crucial component on which a dynamic programming solution is based, a recurrence equation that expresses the optimal solution or its value in terms of the optimal solutions to smaller subproblems. Despite the simple reasoning that led to this point, 6.1 is already a significant development. It directly gives us a recursive algorithm to compute OPT of n, assuming that we have already sorted the request by finishing time and computed the values of P of j for each j. Now compute opt of j. If j is equals to 0, then we return 0, else we return the maxima chosen between the Vj plus compute OPT of P of j or compute OPT of j minus 1. And if the correctness of the algorithm follows directly by induction on j. 6.3. Compute OPT of j correctly computes OPT of j for each j equals to 1 to 3 until n. Prove by definition OPT of 0 equals 0. Now take some j which is greater than 0 and suppose by way of induction that compute OPT of I correctly computes OPT of I for all I which is less than j. By the induction hypothesis, we know that compute OPT of P of j is equals to OPT of P of j and compute OPT of j minus 1 is equals to OPT of j minus 1. And hence, from 6.1, it follows that OPT of j is equals to the maxima chosen between Vj plus compute OPT of P of j and compute OPT of j minus 1, which is equals to compute OPT of j. Unfortunately, if we really implemented the algorithm compute OPT as just written, it would take exponential time to run in the worst case. For example, see figure 6.3 for the tree of calls issued for the instance of figure 6.2. The tree widens very quickly due to the recursive branching. To take a more extreme example, on a nicely layered instance like the one in figure 6.4, where Pj is equals to j minus 2 for each j equals to 2, 3, 4, and so on until n, we see that compute OPT of j generates separate recursive calls on problems of size j minus 1 and j minus 2. In other words, the total number of calls made to compute OPT on this instance will grow like the Fibonacci numbers, which increase exponentially. Thus, we have not achieved a polynomial time solution. Memoizing the recursion. We are not so far from having a polynomial time algorithm. A fundamental observation which forms the second crucial component of a dynamic programming solution is that our recursive algorithm compute OPT is really only solving n plus 1 different subproblems. Compute OPT 0, compute OPT 1, and so on until compute OPT n. The fact that it runs in exponential time as written is simply due to the spectacular redundancy in the number of times it issues each of these calls. How could we eliminate all this redundancy? We could store the value of compute OPT in a globally accessible place the first time we compute it, and then simply use this pre-computed value in place of all future recursive calls. This technique of saving values that have already been computed is referred to as memoization. We implement the above strategy in a more intelligent procedure, mcompute OPT. This procedure will make use of an array m of 0, 1, 2, 3 until index n. M of index j will start with the value empty, but will hold the value of compute OPT of j as soon as it is first determined. To determine OPT of n, we invoke mcompute OPT of n. Mcompute OPT of j, if j is equals to 0, then return 0. Else, if m with index j is not empty, then return m of j. Else, then we define m of j is equals to the maxima chosen between vj plus m compute OBT of p of j and m compute OBT of j minus 1. Finally, we return m of j. Analyzing the memoized version. Clearly, this looks very similar to our previous implementation of the algorithm. However, memoization has brought the running time way down. 6.4. The running time of m compute OBT of n is big O of n, assuming the input intervals are sorted by their finishing times. Proof: the time spent in a single call to m compute OBT is big O of 1, excluding the time spent in recursive calls it generates. So the running time is multiplied by a constant times the number of calls ever issued to m compute OBT, since the implementation itself gives no explicit upper bound on this number of calls. We try to find a bound by looking for a good measure of progress. The most useful progress measure here is the number of entries in M that are not empty. Usually this number is 0, but each time the procedure invokes the recurrence, issuing two recursive calls to m compute OBT, it fills in a new entry and has increased the number of filled in entries by 1. Since m has only n plus 1 entries, it follows that there can be at most big O of n calls to m compute OBT, and hence the running time of m compute OBT of n is big O of n as desired. Computing a solution in addition to its value. So far, we have simply computed the value of an optimal solution. Presumably, we want a full optimal set of intervals as well. It would be easy to extend m compute OPT so as to keep track of an optimal solution. In addition to its value, we could maintain an additional array S so that Si contains an optimal set of intervals among the set 1 to 3 until I, naively enhancing the code to maintain the solutions in the array S. However, would blow up the running time by an additional factor of big O of n. While a position in the M array can be updated in big O of 1 time, writing down a set in the S array takes big O of n time. We can avoid this big O of n blow up by not explicitly maintaining S, but rather by recovering the optimal solution from values saved in the array M after the optimal value has been computed. We know from 6.2 that J belongs to an optimal solution for the set of intervals 1, 2, 3 until J if and only if Vj plus OPT of P of J is greater than or equals to OPT of J minus 1. Using this observation, we get the following simple procedure which traces back through the array M to find the set of intervals in an optimal solution. That is the following procedure. Find a solution of J. If J is equals to 0, then we output nothing. Else, if Vj plus M of P of J, the array M with the index P of J, which is greater than or equals to M of j minus 1 index, then output j together with the results of a find solution of p of j. Else, we output the result of find solution of j minus 1. Since find solution calls itself recursively only on strictly smaller values, it makes a total of big O of n recursive calls, and since it spans constant time per call, we have 6.5. That is, given the array M of the optimal values of the subproblems, find solution returns an optimal solution in big O of n time.